Hi, I'm Oliver, and I'm very excited today to be presenting on Egglog, our new language for performing a quality saturation or working with egraphs. So this is going to be a little tutorial about how to use Egglog, and a big thanks to the rest of the Egglog team. We've been working very hard on this for the last year, and a super special shout out to Saul for making the cool visualizations I'm going to show today. Also thanks to Anjali for giving me feedback on this presentation. So let's jump right in. So why Egglog? Well, let's compare Egglog to a traditional egraph library, Egg. So Egg is a library written in Rust, and that means that you can do anything you can do in Rust as a general programming language. But we actually think that Egglog as a language has a big advantage here. One reason is that as a language, you can write things in a convenient syntax, which is specially tailored for equality saturation workloads. So on the left, you have a pile of Rust code with like a macro in there, and you have to make a runner and that sort of thing. But on the right, we have a nice clean S expression-based syntax for writing down your application. But I think besides that surface level difference, the main benefit I see for Egglog as a language is that now there's a clean abstraction layer between the client, the user who's writing Egglog code, and the Egglog backend. So now we can translate or compile all of your Egglog code into something that's very efficient to execute, and it has a clear abstraction layer on what you can and can't do with the egraph. This is very nice for the backend. So let's move on from Egglog as a language. I think you'll get a feel for why we think it's so good in the rest of this tutorial. But the next big difference is that we've been borrowing a lot of really cool techniques from the database community in our design of Egglog. So a year ago, we had this paper that showed that performing e-matching, or like the main search algorithm over egraphs, can be done very efficiently using database joins. And this, in Egglog, this is going to have a big impact on analyses. So analyses, or e-class analyses, we called them in Egg, are a way to do semantic inference over the syntactic stuff in your egraph. So you might write this big pile of Rust code on the left that does constant folding, and it has like a make, a merge, a modify. The details aren't important, but what this does is look at the egraph and learn something semantic, in this case, how to constant fold things that are in the egraph. On the right-hand side, you see some Egglog code, which does the same thing but much more elegantly. So in Egglog, we've generalized rewrites to do all sorts of things, and now you can just put the primitive multiplication and plus right in the rewrite, and you can also compose these rewrites with other analyses that you have in the database. So I'll get into that later. Another big benefit that comes from this database point of view is that in Egg, we had these very slow multi-patterns, which were very useful, but sort of unusably slow, because they do a cross product over different parts of the egraph instead of looking at the egraph locally. In Egglog, these are very practical and fast because we use a very nice database join algorithm that was recently released called generic join. So in Egg, if you wrote this multi-pattern, it would probably be pretty bad performance-wise. But in Egglog, our generalized rule form handles these multi-patterns really well, and we'll see some of that today. Okay, finally, Egglog is just faster for another database reason, which is Egg does traditional e-matching, and we didn't try to incrementalize it very much, which means that if you keep track of what has changed between the last time you ran your rules and this time, you can do much better because you won't re-find a lot of the old stuff, if that makes sense. While in Egglog, we've inherited this database technique called semi-naive evaluation, and that allows us to do incremental e-matching. You can see here on a micro benchmark, we get a 3x speed up from Egglog without this incremental optimization, and then a 9x speed up over Egg with it. So it makes a big difference. So now that I've gone over some points of why we think Egg is the future of doing equality saturation, let's switch over to the demo of Egglog. So here on the left, I have a data type, which I call, sorry, let me load the example, Herbie tutorial, right, slide mode. Let's go. So I have a data type called math, and under the hood, if I run this, it'll say, here is a Egglog buffer, and I have here defined a data type called math. So math is a type of expression which has 4 variants. It can be a number with a primitive rational. It can be a variable which is defined by a primitive string, or it can be the addition or division of 2 math expressions. If I run this Egglog code, it says that it declared a sort math, so the type is math, and it declared 4 variants, which the underlying representations of the variants are functions. So it declared 4 functions, but you can just think of this as like an AST or abstract syntax tree, which we're going to be able to manipulate in the database. So in Egglog, there's one global database, and I can insert to that database just by declaring some global constants. So let's define 0 to be the number 0 and insert that into the database. And similarly, we're going to define 1 and 2. And notice that in the visualization box, it shows us what's in the global database. So there's a number node, which points to the primitive 0. And let's do the same for 2. There we go. Okay, and besides adding these primitives to the database, we can also add something more interesting. So let's add 1 plus 2 to the database just by putting it at the top level here. And we have this new add node between 1 and 2. Egglog also allows you to define rewrite rules. So this is a rewrite rule as you would expect. It has a left-hand side, which is a pattern. This pattern matches any addition between 2 things, A and B. And it has a pattern on the right-hand side, which is the addition of B and A. And what rewrite says is that we should search the database, and for every match, we add the right-hand side here, and union that newly added right-hand side with the left-hand side. So in the equivalence relation in the database, these 2 things will become the same. The rewrite rule doesn't run when we declare it. It runs when we fire the run keyword. So let's run all our rules once, and in this equivalence class, these 2 add expressions are now the same. Okay, next let's do something a little bit more interesting. We have here on the right-hand side a primitive addition between 2 things. So this rule matches on any addition between 2 numbers in the database and constant folds it into a number which is the constant folded version. So if we run this using the run keyword, we will get that 1 plus 2 is equal to 3. And we can run queries over the database to check this. So this checks that 1 plus 2 is equal to 3. And this checks that 2 plus 1 is equal to 1 plus 2. Right, so everything works out as we expect. Here's another rewrite I've written, and this rewrite refers to the global constant 0 that we defined up here. So 0 is the equivalence class right here in the visualization. It's this num node, and this says that a plus 0 is equal to a. But actually all of the rewrites we've defined so far are equivalent to the more general form or rule. So Egglog automatically expands this rewrite into this rule form. And a rule takes any number of patterns, so we could have more things that match on here. And it also takes any number of actions to perform after the pattern is matched. So this says that we match a plus 0, and then we union a plus 0 and a. And that's exactly what this rewrite turns into under the hood. So these 2 are the same. And now let's do more things using this rule form, which is more general than rewrite. So I've pushed the database because we're going to mess with it a bit, and I want to be able to pop back to this same state later. And here is a more complex action. So this rule matches on any number in the database. And once it's matched on the number, it says union our constant 1 with that number over itself. So notice that 1 and this division, neither of those appeared on the left-hand side, but you can just insert them and union them in the action part of the rule. And this is like where the power of Egglog is starting to come in, but we haven't even matched on multiple things yet using a multi-pattern. So if we run this rule, it adds a bunch of division nodes, and all of these division nodes are saying that this number divided by itself is equal to the number 1, right? But some of you may have noticed a problem here, which is we've actually added 0 divided by 0 into the database. And depending on your semantics, this might be very bad and cause lots of unsoundness. So what if we wanted to avoid adding division by 0 to the database at all? Well, we would have to do some difficult analysis, and that's where Egglog really shines. So we can check that we've found division by 0 in the database, and let's pop back up to where we were before. All right, so now I'm going to introduce the function in Egglog. So if you recall at the beginning, it said that it declared a bunch of functions, num, var, add, and division. But the more general form function allows you to do some cooler stuff. So let's write a function called lower bound, which is a lower bound of some e-class, which is a math expression, and the output is a rational number. So this lower bound is a function from the e-class to a rational. It's a partial function because it may not be defined for every e-class, but when it is defined, it is a rational. And it also has this merge function. So what happens if we find a lower bound between two things? Well, we need to somehow figure out what the actual answer for this function is, and the merge function does that. It says that if you find two lower bounds for the same thing, we should take the maximum one because that's the best lower bound, right? So we define this function, and we'll also define an upper bound, and now we can write rules that compute this lower bound and upper bound in a bottom-up way. So for numbers, we're going to say if we have a rule that is a number, if we match a number in the database, the lower bound and upper bound are the same as the number. Let me just format this in a way that's easier to understand. Okay? So it does two things in the action. It sets the lower bound and the upper bound. For addition, because it's monotonic, we can set the lower bound to the addition of the lower bounds for the children. So this says for any addition in the database, get the lower bounds for A and B, and set the lower bounds for the overall thing to be that new lower bound. So this set keyword is like union, but it's a little more general. It works on any function. So you can think that under the hood, Egglog is going to make a new row for this lower bound table or function. And if it finds a collision, like there's two rationals, it uses the merge function to resolve that. This merge function is really the key to what makes Egglog powerful. Just merge functions gives you sort of everything you need in Egglog, including analyses, and even equality can be done with just these merge functions, but that's another story. Okay, anyways, let's also propagate the upper bound for addition. So this rule does the same thing. It adds the two upper bounds for the addition. And now we can see that the rules we've defined will in fact compute lower bounds and upper bounds. So let's add a variable x to the database. You can see we have this variable node. If we add x plus 1 to the database, we get this add node. And now let's suppose for some reason the user of Egglog knows that x will never be less than 0. So the lower bound of x is 0. And we'll get this lower bound node which says that the lower bound of x is 0. Let's also set the upper bound of x to 1 and run our rules. So running our rules, a bunch of stuff happens, and the visualization's slightly broken. But you can see that the key thing is that we've calculated a bunch of lower bounds and upper bounds, and the lower bound for our addition is 1 because we added 1 to x. Right? So this lower bound node, it's hard to see, is pointing to the addition and 1. So if we extract that lower bound, it'll be 1 in the log here, and the upper bound will be 2. And now we can leverage our analysis that we've been building up of lower bounds and upper bounds, also called an interval analysis, and do our division rule from earlier soundly. So here's finally the payoff. We have this rule form. It says that suppose you match some expression which is a number, and the lower bound for that expression is greater than 0, and we're filtering here in the left-hand side with the primitive greater than. Well then, if this rule fires, we can union 1 with the expression over itself. And this is sound because we've proven in Egglog that this expression can never be 0, so this won't add a division by 0 into the database. So, sorry, this is just the same rule as above, but for addition. And if we run this rule, we indeed see that it adds a bunch of division nodes, but none of them are unsound. We can also check that we didn't insert x over 0 into the database. So we can check that division by anything of 0 is not in the database with this fail command. So if I run this, it says command failed as expected. So that concludes our tutorial on Egglog. I hope that this was exciting to you and you will consider using Egglog for your next project. I will warn you that Egglog is very unstable right now. We're changing a lot of things in the back end, but we encourage people to use it because we think it's strictly superior to Egg. And if you want to read the paper, it turns out it's also superior to another language called datalog, where we drew a lot of inspiration from. So thanks for watching, and bye-bye.